Hello, everyone. My name is Arturo, and welcome to my presentation. Thank you all for coming. So this speech is going to be about generative adversarial networks applied to the medical industry. And, well, this is the content of my presentation, and this is kind of like the output of one of the projects. First, I want to start describing what is a generative and a discriminative model. We're very used to discriminative models, okay? We're used to classify images with labels of cats and dogs and so on. So in this particular case, we want to estimate the probability of having the label Y, given that we have the input X, okay? In generative modeling, it's a little bit different. We want to estimate the probability of having an X example, and, well, knowing that the sample actually exists. So this is like a graphic description of what I just said. In the left side, there is a discriminative model where you just want to build a function that separates two classes. In the right side, we have like the distribution of both of the classes. So that's like the difference. And now I would like to explain what's a generative adversarial network. So this is like a GAN in a nutshell, okay? We have two models. We have a generator that tries to imitate like the distribution of the training samples. And we have a discriminator that tries to decide if the income comes from a real training sample or is actually a fake sample. That's actually the job. So these both networks are training together at the same time, and the goal of both of them is like to do their job, and they both improve through time. So at the end, we reach like an equilibrium where the generator tries to generate like super realistic samples, and the discriminator can decide if the sample actually comes from the training sample or from the generator itself. So this is like the analogy. We have a generator, which is a counterfeiter that tries to generate fake money. And we have like a police, which is the discriminator, that they only want like real money to be like circulating and tries to capture fake money. So if we assume that like they have unlimited capabilities, they both get better as they train. And well, the thing is that at the end, the generator is gonna like create fake money, and it's gonna be like you can't see the difference between both of them. So this is like a graphical description of how the GAN can work. So this is called the GAN lab, and we can visualize like how the training process goes. And let's pick a data set, this circular one, and let's start training. So you can see the epochs running here. And you can see the real data over here. The generator just receives random noise and tries to generate like plausible samples that could be like indistinguishable from these ones, okay? So if we can see that they come like they take these places around here, like they look like real samples, okay? So you can see the noise coming over here, the samples generated, the discriminator trying to decide if some of them are real or fake. And you can see like the feedback, which is the loss function, going back to the discriminator. And the same over here, like you can see the fake samples going over here and giving feedback to the generator. And this process goes on until we have like very good training samples. We can see that we can have like decent samples over here, so it's kind of working okay so far. So this is so you guys could see it, and this is another, like a link created by NVIDIA that shows people that actually don't exist. And all those images are created by generative adversarial networks, okay? And if I press F1, I can get a new image. And so it's kind of cool, like you can see like the quality of the image, and it's actually a fake one, you know? It's created by a neural network. At some point, at the future, we wouldn't recognize if an image is real or fake if it's generated with this quality. We can have another example here of how this works, another generative adversarial network. We can have this, like this picture, and we can select like, okay, I want more sky over here. And you know, it's generating a new image. We can have like more bricks in the, like in the structure of the building. Maybe I can create, you know, more grass over here. So it's like, you know, it's a cool application maybe for designers. Like it improves their capabilities. And this is like my last sample. It's like a generator of images of cats. I just need to clear this, and I'll do my best to create a cat, okay? The idea is that it's going to generate a cat from these edges that I'm going to draw. Okay, let's do it. Let's see what this produces. Yeah, so that's a cat. So I hope everyone has a good intuition of what is a generative adversarial network so far. There are a wide variety of applications here. Like I couldn't mention of them all in this presentation because I have limited amount of time, but I can show you some samples. So this is an example of a conditional GAN, and it uses images instead of noise as an input vector, and it translates into another image. You can have it to create like cartoons or Pokemons. You can even introduce some text describing what you want in your image, and you can have the actual image that you wanted. You can have images of person aging. Super resolution, so you can, for instance, say in the low resolution image and consume less bandwidth. And you can have a better, if you have a generative adversarial network, improve the resolution in the other end. You can try to recreate what's going to be the next frame in a video. And you can, from two-dimensional images, you can try to create a third-dimensional image, which is kind of cool. Some other applications besides the image domain is the creation of drugs. So you can have a generative adversarial network to create the next cure of an important disease. You can try to simulate physical, like, you know, stuff with generative adversarial networks. And finally, and I think this is very important, this is models for reinforcement learning, environments for reinforcement learning. And you usually can run a reinforcement learning algorithm like in real time. You need an environment in order to make, like, you know, parallelization and train the algorithm faster, you know, make your agent interact with your environment and get feedback. So it's very important for reinforcement learning. And well, I just want to invite you to visit the GANs too. This is a website on GitHub where you can visit like many papers related to generative adversarial networks. So yeah, that's like a great resource of information. Now I want to focus on my project. I wanted to recreate, generate artificial images of magnetic resonant images. So some of them have tumors. Some of them have ischemic stroke lesions. And well, basically, we're using generative adversarial networks to generate some of them. So you can see, like, you have a random input, and you can have deconvolutional neural networks in order to recreate the image itself. And this is the generator part. In the discriminator part, you just have regular convolutional neural network and you try to decide if the image is fake or it's real. So this is the architecture. You can see that we perform batch normalization a lot in the discriminator and also in the generator. You have regular convolutional neural networks. And yeah, so this is basically the architecture. The generator uses transposed convolutional or the convolutional networks. It also uses batch normalization. And you can see that the activation function is the hyperbolic tangent because you need to have a range of from -1 to 1 in your pixels. And well, this is the training process of the generative adversarial network, the discriminator loss and the generator loss. And this is like the actual samples. Like you can see like in the few epochs, in the first epochs, you can see like random noise as the output of the generator. As the training process continues, you can see like more realistic images, and at the end, you can see very good samples of it. And you can perform something called explore the latent space, because you can have in the input vector like a representation of an actual image. So maybe if you have worked with text, you can see this experiment run before. You can have an input vector that represents a man with glasses and subtract the vector that represents a man with no glasses, add the vector with a woman without glasses, and at the end having, you know, this woman with glasses. You can actually perform something similar with this data set. And so for instance, you can capture like very weird disease and perform some small variations in order to improve your data set. So that's very good for data augmentation. So the application of this project is like, if you want to use the more robust like convolutional neural networks architecture that are so deep, you need a lot of data. So generative adversarial networks is very good for that. It's going to improve your data set, and it's going to be better than performing like normal data augmentation with cropping, translation, or flipping your image. Because these images with this kind of data augmentation are very correlated, and then they're not going to help you improve your project very much. So in the previous case where you can like find in latent space like weird disease, you can use a GAN in order to perform, like improve the balance of that disease and generate more training samples of that. And well, something sensitive in images of medical industry, they are very sensitive with privacy. So using a GAN, you don't compromise the information of the patients. So in order to perform segmentation, we can use like a different architecture. We don't input an image. But I'm sorry, you don't input the random noise, you input an image, and you use an encoder-decoder architecture for the generator and a UNet for the discriminator. So this is kind of the output. And yeah, that's very important. It's very valuable information for the doctors, so they can perform like more, like better diagnostics. And well, for instance, diagnostics in ischemic stroke is very sensitive in time, because patients can have permanent damage or even death. So the faster we diagnose the disease, the better for us and for the patient. And I would like to finish with some GAN hacks about how to perform like better training in your generative adversarial networks. There is actually a website on GitHub that you can explore many of these tips. And that's it. Thank you very much.
Muchas gracias, Arturo. Tenemos unos minutos para preguntas, entonces si alguien tiene una pregunta, por favor levante la mano y vamos a ir hasta ustedes.
Olá, Arturo. Felicitações por tua apresentação, muito interessante. Não sei se tu viste minha charla ayer. Estou trabalhando exatamente em um problema de segmentação, pero em segmentação de sísmica, de geofísica. Nós na NVIDIA temos um trabalho recente sobre peaks to peaks, pero con imágenes HD. No sé si tú conoces este trabajo. Puede ser una dirección interesante. También utilizan GANs, algunas cosas para subir más la resolución, trabajar con resolución más grandes.
Oh, tengo que investigarlo, pues, sí, sería muy interesante explorarlo también.
Sí, porque tú conoces el trabajo de Pix2Pix de Sola. Y Sola es el trabajo original de Pix2Pix, pero tienen problemas con las resoluciones más grandes. Entonces tenemos un trabajo de NVIDIA que es Pix2Pix HD. Entonces tener informaciones muy interesantes.
Vale, muchas gracias. Qué interesante.
Thank you. So you showed an image both talking about the encoder decoders and UNets. Have you played around with both of those?
Sorry?
Encoder decoders and UNets.
Yeah.
Have you worked with both of those?
Oh yeah. That's you can use, like, because you're performing segmentation, you can use like a convolutional, like a binary classification in order to perform like the work of the discriminator. It's better to use a UNet. And in order to perform a label for every pixel, we use a encoder-decoder architecture.
Okay, thanks.
En español o en inglés?
Como quieras.
So you talk about like binary classifications basically, but have you used this for multi-class classification where you don't just like generate images for a particular kind of disease, but multiple?
Bueno, la idea es que pues se usa una entropía categórica de múltiples clases, ¿no? La idea es que él encuentre, pues compare, ¿no?, entre las diferentes categorías y produzca la salida que tenga que producir.
Pero hasta ahora solo has trabajado con, digamos, algo bien específico, como un, no sé, cisto o algo así.
¿Solo con imágenes médicas?
No, pero me refiero a la enfermedad. ¿Es una enfermedad la que has testeado o como podría
yo tengo como el feedback de lo que tengo que segmentar, entonces lo comparo con lo que quiero y pues la red generativa tiene que actualizarse con lo que necesito.
Ya.
Pues tú mostrabas las imágenes, digamos, en un corte horizontal, la mayoría de las imágenes, pero se puede generar la misma enfermedad, digamos un tumor, en el mismo lado, en corte horizontal y en corte vertical, sagital.
Sí, depende de los datos con los que lo alimentes, ¿no? Si incluye cortes sagitales o verticales, pues está bien, lo sacas de ahí y debe hacer el mismo trabajo.
Pero en el mismo lado específico quedaría, ¿cierto?
Tiene que ser, sí.
Listo.